Welcome to this explainer. Today we're going to peel back the layers of your car's dashboard to reveal the absolutely fascinating engineering behind a feature we all kind of take for granted, cruise control. We're going to trace this journey all the way from the clunky mechanical cables of the past straight into the artificial intelligence of the future. So, let's just dive right into this by asking a really simple question. How does a modern vehicle manage to effortlessly glide down the highway without you ever having to touch the gas pedal? I mean, you just press a button, and suddenly, boom, you're cruising. But right behind that simple button press is this massive, hidden symphony of physics, electronics, and math.
And let's take it a step further. Just think about the complex physics your car is instantly solving. When you hit a steep incline, gravity is literally trying to pull you backward, and wind resistance is pushing hard against your bumper. Yet somehow, the speedometer stays locked at exactly 70 miles per hour, making you look like a total driving prodigy. How does the car actually know exactly how much throttle to add?
Well, to answer that, here is our roadmap for today's explainer. First, the basics of cruise control. Second, the math behind the magic. Third, under the hood, hardware. Fourth, the AI driving revolution. And finally, number 5, troubleshooting and system calibration. We're covering the whole shebang, from basic calculus all the way to cutting-edge machine learning.
All right, let's kick things off with Section 1, the basics of cruise control. Now, there is a clear, massive distinction between the two eras of this technology. Standard cruise control is, well, it's kind of blind. It diligently holds a static speed for you, but if traffic slows down, you have to jump in and manually hit the brakes. Adaptive Cruise Control, or ACC, is a real game changer because it adds a brilliant layer of intelligence. Using forward-looking radar and cameras, it dynamically adjusts your speed to maintain a safe following distance. So if the car ahead slows down, your car slows down. And when the road clears up, it automatically accelerates right back to your set speed.
Moving right along to Section 2, the math behind the magic.
Okay, so the absolute secret weapon here is something called a PID controller. That stands for Proportional Integral Derivative. Think of it like a really hyper-focused digital thermostat for your engine. This mathematical algorithm constantly calculates the error between your set speed and your actual speed. So if you're going 65 but you want to go 70, the PID controller uses proportional math to adjust the throttle based on that exact difference. Then it uses integral math to account for historical data, like if you've been on a long hill, and derivative math to anticipate your future acceleration.
Imagine this as a continuous, never-ending feedback loop. The set speed you choose runs straight into the PID brain. The PID then manages the control variable, which is your electronic throttle body, to regulate the speed. That actual speed is then verified instantly by the speed sensor, fed right back to the PID, and the cycle just repeats endlessly to keep your drive perfectly smooth. And then you have the real-world physics that this PID controller is literally constantly battling. Environmental forces are everywhere. You've got normal force and gravity acting vertically. But horizontally, your car's engine force is fighting a constant war against aerodynamic drag and friction. To win that battle, the controller is essentially doing Newton's second law in real time. It balances the engine's propulsive force against environmental drag. By constantly adjusting the throttle input based on those PID calculations we just talked about, the system aims to make the net acceleration hit exactly zero. And once acceleration is zero, you've reached a steady, constant cruising speed. It's literally high-level calculus happening multiple times a second.
All right, let's look at Section 3, under the hood, focusing on the hardware.
Because it all starts right here at your fingertips. Just a simple push of the set button on your steering wheel sends an electrical command straight to the vehicle's central nervous system. It's actually the only human input required for this entire automated chain of events to kick off. The really crucial part is how all these physical components talk to each other. The Engine Control Unit, or ECU, acts as the brain. It takes real-time data from the vehicle's speed sensor. Then, the ECU commands the electronic throttle control to physically adjust the airflow into the engine. And meanwhile, you have brake and accelerator pedal sensors standing by as safety overrides. The second you tap that brake, the system instantly hands manual control right back to you.
Next up, Section 4, the AI driving revolution.
Because we are definitely not just dealing with static math equations anymore. Thanks to machine learning, your car is actively learning to anticipate traffic and even mimic your unique driving style. Instead of just reacting to the car in front of you slowing down, AI actually allows your car to predict a lane change before it even happens, based on traffic patterns.
Big names like Tesla, BMW, and Toyota are leveraging AI to completely upgrade adaptive cruise control. By analyzing millions of driving scenarios, these systems can predict erratic road conditions and optimize your fuel efficiency. They're even laying the groundwork for vehicle-to-everything, or V2X communication. That's our cars will literally talk to each other to prevent traffic jams. It is a massive leap toward fully autonomous driving.
And finally, Section 5, Troubleshooting and System Calibration.
So what happens when this whole incredibly complex system stops working? Well, the issue usually falls into one of 4 categories. It might just be a simple electrical fault, like a blown fuse, or maybe a mechanical breakdown, like a worn wheel speed sensor. Sometimes it's just a software glitch that needs a quick update. But more and more these days, failures are tied to the vehicle's advanced driver assistance systems, or ADAS, like a blocked windshield camera or a misaligned radar.
Which leads us to a really, absolutely critical question. Since modern cars rely so heavily on these cameras and radars, why is ADAS calibration considered the most important step in troubleshooting? I mean, if a system is mechanically fixed, why isn't that enough?
Well, here's why. A radar module that's misaligned by just a tiny fraction, literally a few degrees, changes absolutely everything. If you get your windshield replaced, or maybe your front bumper gets tapped in a parking lot, the sensors can shift. And skipping strict static or dynamic sensor calibration can cause your car to completely misjudge distances. That means your adaptive cruise control might unexpectedly slam on the brakes while you're on the highway, creating a massive safety hazard. The precision required here is just absolute.
And that brings us to the end of our explainer. As we move from those basic mechanical cables into PID calculus and finally into AI-driven predictive algorithms, this technology has totally surpassed what human reflexes can do. But, it leaves us with one pretty provocative question about the future of transportation. As our cars become smart enough to truly drive themselves, are we as drivers actually ready to let go of the wheel? Thanks so much for joining me, and keep asking questions.